Hey everyone, welcome back. So last week I posted on Twitter a tweet, and this tweet ended up getting about 1.1 million views, which was way more than I was expecting. Thus, I feel like there's a lot more people who've now come to my channel through this tweet, so I should probably do a video explaining how I've reverse engineered this EGS52 ECU controlling the 722.6 gearbox, and some of the really cool discoveries I've found, and how that impacts my version of this ECU, the Ultimate NAC52 TCU. Up until now, there was no way of actually getting the decompiler output in Ghidra. Ghidra is a reverse engineering tool written by the NSA, if you don't know, for it to look good. And then I stumbled across this module by a guy called Kehan, and I have been contributing to it since I discovered it, to make some of the output in Ghidra a little bit better. But essentially, this allows for the P-code output in Ghidra to look really good, like actual pseudocode. So this has really helped me. So first of all, let's look at how EGS's software is structured. You see here in the middle here, there's this red bar. This bar represents various parts of the flash. So here you've got the start of flash, and here you have the end of flash at the bottom. So here, this purple stuff here represents functions and code, which are in the bootloader region. So this is when the CPU turns on, it does this, does a bunch of checks, and then we'll jump to main software. Main software here is this second bunch of purple that you see, purple and blue. So this here is the Siemens application layer, and I found that what this section does is this is in control of all of the inputs and outputs on the TCU. It's involved in reading and writing to CAN bus, and also the operating system itself, because it is a multi-threaded environment, all the code for that is here. Now you may notice, what is this big purple section down here? This down here is actually the Mercedes application layer. So Siemens have actually exposed 2 or 3 functions which Mercedes had to implement, which is for their entire gearbox code. So essentially the entire application of actually stepping through the logic of reading everything on CAN, then processing it, then processing all the solenoids as to pressures and stuff like this, and then doing anything else that Mercedes sees fit, is actually all done on one thread. So I can show that here. Let's go to this function I called MBLayer update. This here is the entire Mercedes code, and you can see it's right at the start of this purple section. And what I find interesting, first of all, is that they appear to have left some profiling data inside the software. So I noticed that what they have here is they have these calls to T8. T8 is a timer on the CPU, which is they've configured it to count up in microsecond increments. And so by grabbing the start time before a block and then getting the end time after calling a bunch of functions, they can measure how long this section of code has taken to execute. And then they seem to write it to global memory. And as you can see, there's a whole array here in memory of just a bunch of times. So this is really interesting. They left this profiling stuff in, because normally this stuff is removed. So let's have a look at how the actual code runs. First of all, you will have all of these timers. So EGS works on a concept of timers. You might see this in DUS. In the adaptations view, they call it cycles. Every cycle is 20 milliseconds. So every 20 milliseconds, this MBLayer update function is called. And Mercedes, what they did is they put up a bunch of counters. When a TCU wants to do something over a sustained period of time, it will set a time, say 40 ticks, so that would be 40 times 20 milliseconds. And every single tick, all of these timers here are decreased. I haven't figured out exactly what all these timers do, but they are all decreased. And then when they hit 0, some condition somewhere in the code base is used, and then it will reset the time or do something now that the time is 0, i.e. saying you should do something now. So first of all, you have up here all of your input functions. These essentially take all the data from CAN, from the various inputs on the TCU, and processes them. And also what I find interesting is if, for instance, I look at, where's the accelerator pedal? So what actually they do is they first of all will check if the CAN signal is available. If it's not available, it will mark the signal as invalid, and after a certain amount of time it will mark it as substituted, and then actually go ahead and substitute a value for certain signals. This happens for some of them, like pedal percentage. So in my case, the pedal percentage is actually set to 25% if pedal information is not available on CAN. This is how the TCU deals with situations whereby, for instance, maybe CAN is dead for a few seconds or so. It just substitutes some values. This comes from the CAN bus, well, I called it the CAN bus calibration, but I don't actually know realistically what it is, and we can have a look at that here. It's just a structure with a bunch of values which are for substitution. Now, speaking of this, I thought I'd mention something. You see where we are now in Flash, we're in this section up here. This is where all of the calibrations are stored for EGS, the ones which it will be using now. Now, there is a database of calibrations which is stored lower down in Flash. This whole section here is lower calibrations. And what I found is, if my cursor works... Oh, I can't seem to find it, hang on. Here, cal info array. There is a structure in memory, or in Flash actually, which defines all of the calibrations on EGS. And calibration is essentially a set of data which the SCN coding string, so this is variant coding, will point to. So in our case, I have here all of these calibrations, and for instance, this one's the torque converter settings. Now here, for instance, I can see this is the pointer to memory, this is the pointer to Flash, where all of the calibrations will be stored. And I can see here that they are assigned to index 6 in the SCN coding, so byte 6 in the SCN coding string selects which setting pool to use. I can see that each calibration is 0x134 bytes in size, and there is also 10 different settings. So let's go here and look at the array, and as you can see here, I haven't figured out what all of these settings do, but you can see here's one setting, it's very big, and then here is other one, next, etc. And essentially, each EGS part number comes with a certain pool of information, and this way they can just change the SCN coding string but have one EGS part number for multiple different vehicles, because these settings, I'll get to why they are also necessary in a bit. So essentially this way they can hot swap one EGS part number into multiple cars, just change the SCN coding string which says like select a different data model for each calibration type, and the EGS then actually copies this information to a pointer which points to a higher block of memory up here, where the one which is currently in use is stored. This has got something to do with the way that the C166 CPU does memory addressing. It's just more efficient if all of the calibrations are in one block at the top of memory. Now, what I find really interesting about this is I remember reading on the Mercedes forums a while back that if you decided that you had a tuned 722.6 ECU and you were to, say, add agility mode, which involves modifying the SCN coding string, some people report that what will happen after doing this is their tune has disappeared. And I can tell you exactly why that is. Because I found that whenever you touch the SCN coding string, the EGS TCU will go ahead and re-evaluate this entire calibration pool and copy everything back up here to where the current calibrations are stored. Therefore, if your tuner has only modified your current calibration information and not the default pool information, then when you unmodify the SCN coding string again, it just overwrites all of that tuned information with essentially defaults from the EGS's main memory bank. So that's an explanation for that. Next, I want to talk about something interesting that I found last night. So I found that in the function which processes oil temperature, there is this weird information going on whereby it's checking if the oil temperature is within certain ranges. First of all, I should point out that you actually have to minus 50 degrees from these numbers here to actually get what temperature it's looking at, because all the numbers on EGS are unsigned, they're not signed, so therefore negative 50 is represented with 0, and 50 degrees is represented with the value 100. Don't ask me why they didn't just use a signed number, I don't know. But anyway, what I find interesting is in EEPROM block 7, so the EEPROM, which is the little tiny storage for calibration stuff, it's not part of the EGS's main memory map. It will store all your it will store all your adaptation information, so this is where adaptations are stored, but also it will store your last saved profile. If it's automatic, it does not save if your profile is manual. You might know this if you put your car in manual, turn your car off, turn it back on, it's in sports. Now, what I find interesting is in that same memory block where you have your saved profile, there it is writing an incremental counter depending on the temperature of your oil. And I figured out that what this actually is runtime stats. It is never accessed by DAS, and I know that because with references to this memory block, it's only referenced in this function here, process oil temp, and in the function which processes profile switch because it needs to know which one was last used, and not by any of the diagnostic functions. Compare that to a couple EEPROM blocks above, and you can see, for instance, EEPROM block 5, which is for some, I think it's torque converter adaptations, I'm not sure, but you can see it's read by KWP read data by local identifier function, which I identified as that. So this can be accessed through diagnostics, whereas this area here cannot be accessed by diagnostics. So I don't know why they left this counter, or what the purpose of these counters are for, but it's interesting because it is gathering statistics on how long your gearbox is operating with certain oil temperatures. So you have a category here for when your oil temperature is less than 100 C, when it's less than 120, when it's less than 140, and when it's more than 140. And I did the statistics by adding these two numbers up, but timesing them by their timer counter by 20 milliseconds, and I came to the conclusion that my original EGS was operating, and bearing in mind only when in drive, it counts this, so it was operating in drive for 5,409 hours over the past 20 years. So that's not too bad. But I would be really curious to see if I could write a tool which could dump this from any EGS, and then I can tell you like how long your car's original gearbox was running for based on this. But maybe this was left over by development, or maybe this was something they were planning to add to DAS for like oil lifetime counter, and they just never got around to finishing the feature. But this is really cool to find these things. Next up, we have the actual function which processes your gear shifts. This function is enormous. And as you can see, this switch statement thing here is actually not quite passed correctly. Actually, this is never passed correctly by the Ghidra plugin because of the way that the C166 does this really weird memory indirection. It's actually impossible for Ghidra to calculate some of these values natively. So I actually ended up writing myself my own script for Ghidra, which is in Java, unfortunately. I hate this language. But this actually goes ahead and tells Ghidra where the jump table is and where the jump locations are, and therefore it can reconstruct the switch statements for different things. So in this case, all you have to know is that the shift type goes up to the value, I think, I can check here. It goes up to the value of 8, and if it is less than 8, then we have all our 8 cases here, so 0 through 7. Unfortunately though, my script does not work for nested switch statements. So here you have a switch here inside an existing switch statement. So unfortunately my script does have some limitations. I am working on trying to figure out how to fix that. But anyway, next up. So here we have a function at the end. So at the end of every single cycle of this function, it will calculate the current request to send to the shift pressure control and modulating pressure control solenoids. This function is fairly complicated and actually references the calibration information quite a bit. Now this is my next point I want to talk about here. So a lot of people have asked me why my TCU does not work perfectly in their vehicle when it does in mine or it does in someone else's car, and this is purely down to the number of models that there are. So essentially, I suspect based on the way that this code has been written that it's probably auto-generated by something like Simulink back in the late 90s. And essentially what the TCU is doing is it's actually mathematically simulating the entire gearbox and then just outputting according to these maths models. Because of that, you change one thing, like you change the weight of your car, or you change a clutch packet in the car, you have to update the entire model. And the model is all of these calibrations. This is why I'm trying to reverse engineer the module, because I'm trying to find where all these calibrations are, what they do, so then I can add them to my TCU, so hopefully everyone has a more unified experience with the TCU. Also, one thing I want to talk about here, which is why I think this is all auto-generated, is because you have crap like this coming up in the codebase, where you are moving 0 into a register, then you are moving another value into here, then you are multiplying R3 by R15, which in this case is 0, and then it is actually taking these values out. So bear in mind this is 1, 2, 3, 4, 5 instructions. Now, any modern compiler will just say, well, he's multiplying by 0, so the answer will be 0. It doesn't matter what you move into anything else here, it will just be 0. So, in a way, this is extremely unoptimized code, because you are making the processor do things wastefully, when any modern compiler would have just said that's 0, and we can only just put one instruction there, which would be, in this case, move R15 0. Don't know why so it looks like what they've done is they've left all the compiler optimizations off, which has actually made my life a lot easier reverse engineering this module, purely because you can essentially see very verbose code output. Again, here another function which relies very heavily on calibration information is to calculate the amount of torque that should be removed from the off clutch to get it to start releasing from the gearbox. These reference quite a few calibrations, and again, if this is not perfectly matching up to your car's characteristics, then the results are not perfect. And yes, in my EGS, what I've done is I've actually tried to generalize a lot of the values whilst I'm still trying to figure out what these calibrations do, and some people have reported that's helped quite a bit. But yeah, it's just an absolute mess of trying to figure out what all these values do. And then also, to make matters worse, I've noticed that in different EGS part numbers which came later on, they actually changed the structure format. So your values are no longer in the same location in these calibration pools. It's just completely scrambled, and I have to descramble it, put it into a consistent format, then put that consistent format on my TCU for you to use. And this is what the calibration information is in the configuration app. So next I want to show you this. This here is the function which calculates the high time for filling. And high time for filling is when the clutch is being applied, it must be pre-filled up with some pressure. It does this in two ramps, one with high pressure, then one with low pressure, and then it starts moving the clutch on. And what I find interesting here is you see here these two special special cases here for 5 to 4. So it looks like when they were testing this, they found that there was some problem with the 5 to 4 shift, which it wasn't performing adequately with the generalized cases. And what they did is they just patched this. So they said if 5 to 4, then do something else. If 5 to 4, then do something else. So there's all of this weird, like, a lot of the software from what I've found in here seems to be held on with duct tape. Like, there's so many patches for different edge cases that they've put in here. It's crazy. So, lastly, two things. One, I might actually do a live stream where we do some more disassembly of EGS. Let me know if you actually want to see that, and maybe I can plan for a live stream where we tear apart the software a bit more, figure out some more implementations. But next up, I want to show you what I've actually been working on in terms of my EGS based on this disassembly. So, what I've done is to make my life a little bit easier, is based on the reverse engineering code that I'm figuring out, I've actually written a compatibility layer between my way of coding and EGS's way of working. Now this is because on my system I was working in millisecond timers, whereas in EGS we're working on these decreasing counters which count down in 20 millisecond increments. There's a completely different morphology going on compared to what I'm doing. So here in shift_release.cpp, for instance, which is based on the release shift that I've been reverse engineering, which is meant for low loads and when you're kind of cruising, when you're not actually accelerating, I found that it's actually quite nice to make this little compatibility layer whereby you are converting between my style of coding, which is where you use milliseconds for everything, you use like actual accurate timers, and the EGS's way of working. And the reason for this is because if I was to try and rewrite the EGS's code myself and do it using my system, I would have no way of knowing where a bug crept up in. Was my bug because I copied the assembly wrong and tried to re-implement it wrong, or I was referencing a wrong value? Or is it because of my timer system? So therefore, I figured it's actually easier just to write a function whereby it looks like the original output from EGS, and this way you have slightly less chance of there being a bug. And as you can see here, what I've actually done is next to every single value that I'm grabbing from calibration for now, I'm actually referencing where I brought them from. So eventually what I'm going to do is I'm going to then copy these release cals onto the TCU, onto this TCU itself, and then I can reference it from there for everyone to use the preset from their car from Mercedes. So it should help with a little thing. But yeah, like, I've honestly been so busy these past few weeks trying to implement this because it is a lot of work to get this done. And actually only last week I got my car driving with this code because it was so buggy to begin with, because actually what I found is that the disassembly can be quite wrong sometimes, and this is because the C166 has this weird double stack system where you have two stack systems being used at the same time in a function, and because of that, Ghidra sometimes cannot infer which variables you are talking about at certain times, and it gets a little confused. So the assembly looks okay, but then when you actually try to copy the logic which Ghidra says the EGS is doing, it's wrong. So it's a lot of work to do this, but again, maybe I could do this more on live streams whereby we cover disassembling and copying stuff out. So like, here's one function that I haven't finished annotating what all the variables do, because I'm not too sure, to be quite honest with you, what this all does. All that I know is that it works. But yeah, so I think that'll be it for this video. I just wanted to kind of cover everything that I've been doing on the EGS, reverse engineering and implementing it on my own one. There are obviously dev build updates coming out continuously whilst I'm pushing changes here, so if you are a tester or a user of the TCU, feel free to check out the dev build, but please check the Telegram channel, because I do cover things that you can and can't do on these builds, because they are a little bit fragile in terms of when you drive, but I'm working towards a much better goal here, which is essentially, it feels like stock but slightly better. That will be the main goal here. Obviously, if you're new here, feel free to subscribe. I'm going to probably do some more videos on the 2.0 board and how programming in Rust is actually changing the way I think of the TCU. And obviously, then, if you like it, you like it. Feel free to subscribe, and I'll see you in the next one. So, goodbye.